This video presentation is brought to you by the Pro Mathematics Academy.
In this video, we will be looking at multiplication of matrices, and the objectives are as follows. 1. We will look at row vectors and column vectors of a given matrix, and then we will look at the definition of the scalar product / dot product of vectors. Using that said concept, we can then look at what is the meaning or the true process behind multiplication of matrices. Now we begin by looking at a matrix M, which is equal to A, B, C, D, right? And if we look at this matrix, we see that the row vectors of M are 1. We have R1, which is the row vector number 1, being equal to AB, right? And for number 2, we have the second row, which is CD. We write that in vector form. Then we look at the column vectors of M, right? So we say that the column vectors are C1, which is AC, right? That is the first column of M. And the second column vector is the second column of M, right? So we have C2 being equal to BD. Right, now we move on to look at the definition of the scalar product. Alright, so we say that the scalar product of two vectors denoted v1 dot v2 is the sum of the products of the terms in the same positions. Alright, so if we have a vector v1 which is equal to w1 w2 and a vector v2 which is equal to m1 m2, then we can write the scalar product v1 dot v2 as w1 times m1 plus w2 times m2, and this should simplify out to a number c, right, which is a scalar. Hence the process is given its name, the scalar product. All right, once we recognize the scalar product process, we then look at what we call multiplication of matrices. Alright, so here we're given the matrix M equals A, B, C, D, that's M1, and the matrix M2, which is E, F, G, H, right? And we say let N be equal to M1 times M2, which is a product of two matrices in this case, right? Note that N, the resulting matrix, is a 2 by 2 matrix, right? In the form N11, N12, N21, and N22, right? So we have those four terms in those positions. Now we see that N11 is a scalar product of the first row vector from M1 and the first column vector from M2. Missing the N from a column there. Right, so we can write down N1 as N1 equals R1 times C1. This then allows us to write AB dot EF as A times E. Notice that A and E are in the same positions. Plus B times F. Notice in this case also B and F are in the same position. So we're just multiplying elements in the same position across. So we can now write down N12 as R1 dot C2. This means that we now have AB times GH, and notice in this case we are not just saying times, but we're actually saying dot, which is a specific type of multiplication, equals A times G plus B times H, right? Notice that A and G are in the same position and B and H are in the same position. So we're just multiplying elements in the same positions and adding them as we go along. Right? In general, if you want to find the element in the ith row and jth column, we multiply the ith row times the jth column. Sounds a bit funny, but that's actually what it is. So this means the element in the ith row and jth column is the scalar product of the ith row vector from the first matrix and the jth column vector from the second matrix. All right, sounds like a mouthful, but we'll go into some specific examples. Here we look at our first example, which is 1, 4, -2, 3 times 1, 6, negative 1, 1. Right? And the first step when multiplying matrices, we want to separate our rows in the first matrix and our columns in the second matrix. Okay? So this then gives us 1, 4, negative 2, 3 times 1, 6, negative 1, 1 separated into columns and rows, which is now equal to the first element in n in the resulting matrix. It's going to be the first row from the first matrix times the first column from the second matrix, right? So that gives us 1 times 1 plus 4 times negative 1. The second term here in our resulting matrix will be n1, 2, which is the first row from the first matrix times the second column from the second matrix, right? This then gives us 1 times 6 plus 4 times 1. And now we calculate the third term in our resulting matrix, which is a product of the second row from the first matrix times the first column from the second matrix. This then gives us negative 2 times 1 plus 3 times negative 1, right? And the fourth and final term in our resulting matrix is given by the second row in our first matrix times the second column in our second matrix. This is negative 2 times 6 plus 3 times 1, right? Simplifying this gives us 1 minus 4, 6 plus 4, negative 2 minus 3, negative 12 plus 3, which then can be simplified to negative 3, 10, negative 5, and negative 9. That is our answer. We then jump into our second example. Here we have the matrix 1, 2, 3, 4 being multiplied by negative 1, 0, 1, 2. The first step, as usual, is to separate our first matrix into rows and our second matrix into columns. So we see that we have 2 row vectors and 2 column vectors. The first element in the resulting matrix here will be given by the first row in our first matrix times the first column in our second matrix. This gives us 1 times negative 1 plus 2 times 1, right? The second element here is the first row in our first matrix times the second column in our second matrix. This is 1 times 0 plus 2 times 2. The third element is the second row in our first matrix times the first column in our second matrix. This gives us 3 times negative 1 plus 4 times 1. And our final element here is the second row in our first matrix times the second column in our second matrix. This gives us 3 times 0 plus 4 times 2. Simplifying gives us negative 1 plus 2 for our first element. Second element is 0 plus 4. Then we have negative 3 plus 4 as our third element, and our fourth element is 0 plus 8. Simplifying even further, we end up with 1, 4, 1, and 8.
That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.